In a previous presentation, we outlined the concept of momentum and undertook some basic questions, calculating momentum, resolving momentum in various components. Here we're going to use the concept of momentum to analyse collisions or impacts. So in a collision between two bodies, each body will exert an equal and opposite force on the other, Newton's third law. Each force acts for the same time period, and thus each body experiences an equal but opposite change in momentum. If momentum of one body increases in the collision, then the momentum of the other body is assumed to decrease by the same amount. Hence, the total momentum remains unchanged. This principle is termed the conservation of linear momentum. In the following questions, we'll be using the notation shown below. As mentioned in our previous presentation on momentum, momentum is a vector property, so we have to account for the direction. So we'll always have a sign convention in our questions. This is showing positive x, so positive velocities or positive momentum in the x direction are from left to right. We will also be considering a before impact scenario and an after impact scenario. So before impact, body 1 shown here will have an initial velocity u1, and body 2 shown here will have initial velocity u2. After impact, body 1 will have a final velocity v1 and body 2 will have a final velocity v2. And that's the notation we're going to use throughout the questions we're reviewing on collisions. The bodies, of course, don't have to be cars, they can be any object, trucks, billiard balls, etc. So considering a collision of the above two cars, on impact, according to Newton's third law of motion, the force on body M2 is equal and opposite to the force on body M1. So from Newton's second law, we reviewed in a previous presentation of force equals mass times acceleration, we could write that the force for body 1, its mass multiplied by its acceleration, is equal to negative mass 2 multiplied by the acceleration 2. So if the impact occurs in time t, then we can rewrite the above equation in terms of the change in velocities. So instead of writing m1a1, we could actually write m1 and then the change in velocity divided by the time taken would be the acceleration. Likewise, on the right hand side, we can have negative m2, and again, that's multiplied by the change in velocities divided by time taken, which is acceleration 2. We can clearly see that the t's cancel both sides of the equation, and rearranging the equation, we can form the expression of m1 multiplied by u1 added to m2 multiplied by u2 is equal to m1 multiplied by v1 added to m2 multiplied by v2. In other words, this equation states that the momentum of the two bodies before impact must equal the momentum of the two bodies after impact. This equation also assumes that the two bodies have different velocities after impact. In some of the questions, the objects, the cars in this case, can be locked together after impact, and this slightly simplifies the expression. So now we could write that the m1u1 added to the m2u2 is actually equal to what I've termed m3 multiplied by v3, where m3 is actually the mass 1 added to mass 2, and the v3 is the common velocity of the masses 1 and 2. So the first equation is more generic, and it assumes that the bodies after impact have different velocities. The second equation shown here assumes that the bodies after impact are locked together and so have a common velocity. Here's a suggested procedure for the impact calculations. Step 1, we should draw a simple diagram of the objects which comprise the system under consideration. 2, we need to state the positive coordinate system to be used. So in this case, the positive x and the positive y are shown in the diagram. Step 3, above each object we should mark the initial velocities, and below them we should mark the final velocities. These are shown in the positive direction, or our sign convention shown here, coordinate system. Step 4, we should write down the conservation of momentum equation and substitute values into the equation. And step 5, we should rearrange the equation and solve for the particular unknown we're trying to find. The following example outlines this process. Example 1. A body of mass 2 tons is moving with velocity 10 meters per second to the right. It collides with a body of mass 5 tons moving at 12 meters per second in the opposite direction. If the bodies move with a common velocity after impact, we're required to calculate this velocity. So from the information in the question, body 1 has a mass of 2 tons and it's travelling at 10 meters per second from left to right. Body mass 2 is 5 tons and that's moving from right to left at 12 meters per second. Notice the positive direction shown is from left to right. So body 1 is moving with a positive velocity, but body 2 will be moving with a negative velocity. After the collision, both bodies have the same velocity. I've called it V3 here. So the mass of body 1, M1, is 2 tons. The mass of body 2, M2, is 5 tons. The initial velocity of body 1, U1, is 10 meters per second. That's positive. The initial velocity for body 2, U2, is negative 12 meters per second. Be very careful you insert the negative for U2. It's going in the opposite direction to the positive sign convention we're using. The combined mass after impact, M3, will be 7 tons. That's M1 plus M2. And the velocity after impact we're trying to find is V3. So considering the principle of conservation of linear momentum, I'm using the equation M1U1 added to M2U2 is equal to M3V3. I need to transpose to find the final velocity, the V3 in this case, so I simply divide both sides by M3. And that's what's shown here. Notice use of the bracket. I now have M1U1 added to M2U2. It's all divided by M3. Please note that the bracket is essential there to have. Inserting the above values here into the equation, and again it's very important to notice the negative has to be accounted for the U2 value here. When you evaluate, V3 is equal to negative 5.714 meters per second. The negative simply means that when the two bodies are locked together after impact, they will be moving with a common velocity from right to left, going against the positive sign convention shown. And that's understandable because the initial momentum for body 1 is 2 times 10, that's 20 units. And the initial momentum of body 2 is 5 times 12, so that's 60 units. So there's greater momentum in body 2 than in body 1. The question does want the answer in terms of kilometers an hour. Of course, we can use the appropriate conversion. So negative 20.6 kilometers per hour. Now, one thing to notice in that question is that I did not change the tons into kilograms. In the majority of our lectures, we would always convert tons to kilograms to undertake the calculations. But in this particular example, we can actually get away with using tons because the mass unit cancels out due to the equation having mass on both sides. So even if I'd converted the tons to kilograms, I would have got exactly the same answer. It's just that I would have factored up the numerator by 1,000 and I'd have factored the denominator by 1,000. So the units still cancel out. And the same is true for kilometres an hour. I generally always encourage you to convert kilometres an hour to metres per second, but if you were given kilometres an hour as the velocity of the bodies, you can actually use that in the calculations, because again the unit cancels out. You will see that illustrated in later questions. Exercise 6. I should say first of all, don't try this at home. An airgun pellet of mass 10 to the negative 3 kilograms is shot into a piece of plasticine on the back of a stationary toy truck, which together weigh 0.499 kilograms. That's the combined mass of the plasticine and the stationary toy truck. If the truck and the plasticine move off together at a speed of 0.5 meters per second, we're asked to calculate the initial speed of the pellet before it hits the plasticine. Answer is stated in the brackets here. To undertake this question, we're going to use the principle of conservation of linear momentum. Because the pellet is lodged in the back of the plasticine on the truck, we can see that after impact there is a common velocity. So we can use the simplified linear momentum equation. In this case, the m1u1 plus m2u2 is equal to m3v3. If you think you can attempt this question without further assistance, I would encourage you to stop the presentation and attempt it now. But the full solution will be shown on the following slide. Exercise 6, the first thing I've done is to extract the information from the question, quite a bit of information here. So from the question, the pellet has a mass of 10 to the negative 3 kilograms. So M1, the mass of the pellet, is 0.001 kilograms. The plasticine and stationary toy truck together weigh 0.499 kilograms. So I've called the M2 is 0.499 kilograms. And we're also told that the toy truck in the plasticine is initially stationary, so U2 will be 0 in this case. We know that after the impact there is a common speed of 0.5 meters per second as the pellet is now lodged in the plasticine on the back of the truck. So I've stated V3 as 0.5 meters per second. The common mass after impact, of course, will be M3, and that'll be 0.5 kilograms. Now, the question wants us to calculate the initial speed of the pellets. So we're trying to calculate U1, shown in our diagram here. Just note for reference, our sign convention is left to right is positive for both velocity and momentum. So, applying the conservation of linear momentum, I'm using the equation m1u1 plus m2u2 is equal to m3v3. And that's because both bodies are joined together after the impact. All I do now is rearrange. So I subtract the m2u2 for both sides, and then I divide throughout by the m1. For calculating u1, I simply put in the values. So m3 in this case, the combined mass of the pellet, plasticine and truck is 0.5 kilograms. And in this case, the initial velocity of the truck and the plasticine is 0. As we're told, the truck is initially stationary. Hence a 0 in our equation here. We simply then divide by the m1, which is the mass of the pellet, which is 0.001 kilograms. Evaluating the speed of the pellet, it is 250 meters per second. And if you divide the 250 meters per second by 1,000 and multiply by 3,600, you'll convert the velocity U1 into kilometers an hour. And you'll find it's 900 kilometers an hour. Question 1c. A wagon of mass 3.2 tons is moving with initial velocity u when it collides with another wagon having a mass of 3.4 tons moving in the same direction but at 3.6 kilometers an hour. After impact, the wagons have a common velocity of 12.3 kilometers an hour. We're asked to determine the initial velocity of the first wagon. This question is very similar to the example on the previous slide, so I'd encourage you to stop the presentation and attempt this question using the same method as we've applied previously. The answer is shown here for reference. The full work solution is shown on the following slide. Question 1c, here's the full solution, and it's a very similar solution to that shown in exercise 6. I'll let you review this solution at your own pace. And here's question 2c. I'll let you read this for yourself, and I'll encourage you to stop the presentation and attempt the question. Read the question carefully and account for the directions as stated. The answer is shown here. The full work solution is shown on the following slide. Question 2c, here's the full work solution. Again, be very careful in this question. Before impact, the two vehicles are travelling in different directions. Lorry A is moving from left to right. Lorry B is moving from right to left. So once we've stated our sign convention for positive directions, we need to ensure we account for that. So in the calculations, you must have a -3 used, or else you'll calculate the wrong answer. Again, the negative final answer indicates the direction of motion for the lorries as they're joined together. I will leave you with some further tutorial questions, question 3c through to question 6c. And again, the answers are shown in the brackets on the right hand side against each question. Here is the full work solution to question 3c shown here. I'll let you review this at your own pace. Notice in this question the wagons are not joined after impact, so we are trying to find the velocity of wagon 1 after the impact. It's v1. Question 4c, full solution shown here. Again, I'll let you review this at your own pace. Here the vehicles are locked together after impact. We're trying to find the common velocity after impact. And question 5c, full work solution shown here. In this question we're asked to find the mass of the first body given the information in the question. And when you apply the conservation of momentum equation in this particular case, you're trying to find the value of m1, and mass 1 occurs on both sides of the equation. So in this question you'll need to rearrange the equation to get all the m1 terms onto one side of the equation. Then you'll need to factorize on m1 and then rearrange the equation for m1 to eventually find the mass of body 1 in this particular case. So slightly more complicated transposition here. Here's the bibliography used to help generate this presentation.